Okay. So let's move on then. So, okay, to prove the second part. So the second claim is that this compatibility of the Jordan decomposition with homomorphisms of groups, of algebraic groups. So the first thing we do is we factor phi as the following. So we first have a surjection of G onto its image. We know that the image is an algebraic variety and it's closed inside of G prime. And then we embed that image inside of G prime. So this is a bit similar to what we did last time when we had a linear map of vector spaces, except there we had first an injection and then a surjection. Okay, so because we can factor it in this way, it's enough to prove the claim in two cases. So first case is when phi is a closed embedding, in other words, this part here. And the second case will be when phi is a surjection. So that'll take care of this part here. Because we can take the semisimple part and unipotent part in G, move them over to here and use the case 2 to show that we have the appropriate equality, and then use case 1 to show that we have the appropriate equality in G prime, and the fact that phi is this composition gives us the result. Okay, so how do we prove case 1? So if phi is a closed embedding, then G, the affine algebra of G is a quotient of the affine algebra of G prime. So it's the quotient by some ideal I. And we have that G is all the elements in G prime that preserve this ideal. I think maybe Shivi talked about this a little bit in the TA session on Monday. So we have this fact, and then we just do some manipulation. So we can think, if we have an element in G, we can think of it either as an element of G or an element of G prime, since phi is a closed embedding. So if we think of it as an element of G, then we have this automorphism of K brackets G. And if we think of it as an element in G prime, then we have an automorphism of G prime. And how are these two things related? Well, there's a commutative diagram that relates the two. So since we know that this map here, so the G prime map preserves this ideal I, we have this commutative diagram. And so then we use this fact. So we had, I pointed out that this semisimple and unipotent decomposition interacts well with subspaces that are stable. So we can, if we take a quotient like this, then so let's just go through this. So if we take the semisimple part of G, thinking of it as an element in capital G, then by what we argued before, that's the semisimple part of rho G. And then by this commutative diagram, that's so now we write this rho G as this map induced by the rho G for G prime. And then we're taking the semisimple part, and then by our previous results about semisimple and unipotent parts interacting well with quotient maps, we see that this is the induced map by the semisimple part of rho G, thought of as an element in G prime. And then we use the definition of G sub S to put the semisimple part on the G component. So that proves that whether we think of G as an element in G or in G prime, we get the same semisimple part. That's exactly what I wrote here. Okay, so that's a pretty straightforward argument. Hopefully the notation. So case 2 is what happens if this map phi is surjective. So if it's surjective, then then let's see here. Then we know that the affine algebra of G prime is a subalgebra of the affine algebra of G, and it's preserved by any row sub G for any G in capital G. And so now, just like before, we use the results about semisimple part and unipotent parts behaving well under like the induced maps on quotients. Now we use the fact that they behave well under taking invariant subspaces. And yeah, so I didn't include the details. I think it follows pretty quickly from what we argued before. Okay, so that proves this result. Any questions? I got a message that my internet is unstable. Hopefully that was just temporary. Okay. All right, so that proves that. So I want to list a number of other results that I won't go into the details of their proofs. So first of all, if the linear algebraic group happened to be GLN, then the theorem we just proved says that there are these elements G sub S and G sub U for any element in G. But on the other hand, if our group was GLN, then from before we had the multiplicative Jordan decomposition that gave us a semisimple part and a unipotent part, and those are the same. So that's what's claimed here, that it doesn't matter. We get the same thing. Second result is that if we had a semisimple element in a linear algebraic group, then anytime we embed this group as a closed subgroup of GLN, which we can always do as we've shown, then the image of little g will always be a semisimple matrix. And yeah, that pretty much follows from the second part of the theorem we just proved. And a similar result for unipotent elements. So if we have a unipotent element, then its image under any closed embedding will be a unipotent matrix. Right. So yeah, so I won't go into the details of the proofs, but they follow pretty quickly from what we've shown so far. Okay, and so just like we say an element is unipotent if it's equal to its unipotent part, we say that a linear algebraic group is unipotent if all its elements are unipotent. The terminology with semisimple is a bit different, so we'll get to that, but so for the next few pages, we'll be focusing on unipotent groups. So yeah, so all the elements are unipotent. And okay, what's the canonical example of a unipotent group? It's the subgroup of upper triangular matrices with ones along the diagonal. So that's the go-to example if one needs to prove something about unipotent groups. And also any conjugate of this subgroup is unipotent. So it's sometimes confusing. Maybe you think that these are all the unipotent elements of GLN, but they're not, because we can conjugate this subgroup and get more unipotent subgroups. Yeah, it's not a normal subgroup, so we can conjugate and get new subgroups. Okay. And so this proposition we have here is important because it reduces the study of unipotent groups in some sense to the study of UN of this example. So it says that if we have a subgroup of GLN consisting of unipotent matrices, then we can always conjugate this subgroup inside GLN to get a subgroup of UN. So yeah, I mean, we can think of G as the image of a closed embedding of some arbitrary unipotent group, and we can conjugate that image so that it lands inside UN. All right, so how do we prove this? So yeah, we need a few we need a few extra results that we'll see in the course of the proof. So I decided just to include them in the proof rather than separating them out. Okay, so we do this by induction on n. So
I have a question about why it's not simple. You told us before that it is equivalent to say that they are diagnosable to such form, that it's diagnosable and all the eigenvalues are 1. So that's basically what you prove, or?
so I can't hear you very well. Is it?
Do you hear me now?
It's the
Do you hear me?
same. I don't know if it's you and maybe me. So you were asking about something about matrices, unipotent matrices being diagonalizable.
Yes, you already said this before, 2 weeks ago, that all the unipotent matrices those are diagnosable and all their eigenvalues are 1.
Oh, they're not diagonalizable. So unipotent matrices
Okay,
have,
non-diagnosable, right? Okay,
yeah.
thank you.
So the only unipotent matrix that's diagonalizable is the identity matrix.
Okay, thank you.
Yeah. All right. So we do this by induction on n. So first of all, if n equals 1, then there's not much to show because then GL1 is the multiplicative group, and the only unipotent element is 1, and the UN in this case is just identity, so there's nothing to show. Okay, so the induction step, let's take V to be k to the n, and we have this action of G on V, induced by the embedding of G inside of GLN. And so now there are two cases. So the first case is where the action is not irreducible. And here it is, so what does that mean? So that means there's a G-stable subspace W whose dimension is somewhere between 0 and n, not inclusive. So there's some non-trivial proper G-invariant subspace. G-stable subspace. So it's stable under every element in G. So, okay, so then the idea is we apply induction to W and to the action on G mod W. So to make this more precise, let's say M is the dimension of W. So this G-stable subspace. And if we, so there's various ways to do this, but to be a bit more concrete, let's pick a basis for W and extend it to a basis of V. So since G preserves W, that means that every element in G in this basis is of the following form. So here we have the first M vectors, which form a basis of W. And those have to be mapped to themselves. So we have something here and 0 here because they don't, W is preserved. So we can't land outside of W. We can't hit these vectors, these extra vectors. And here we can have anything. Okay, so then basically we have these matrices here and these matrices here, and we want to conjugate them to be unipotent. So okay, so what's going on here? So to make this to put this all together, if G embeds into the subgroup of all matrices of this form, this subgroup of such matrices is isomorphic to GLM, that's coming from here. GLN minus M, that's this part here, and matrices M, and yeah, so it's as a algebraic variety, it's isomorphic. So maybe isomorphic is not the right word to use here, but it's isomorphic as an algebraic variety, not as a group. But still, it's okay because we can project onto GLM, and we can project onto GLN minus M. So we have these two maps, and these two maps will be maps of groups. So yeah, so I apologize. I should have made it more clear here that this subgroup is not, it's as an algebraic variety, but not as a group. But still, these maps phi and psi will be group maps. Yeah, so once we have these group maps, we can apply induction since we have smaller dimensions here. And we can conjugate the image. So we don't look at G itself because it won't embed necessarily inside of GLM and GLN minus M, but its image is just some subgroup. So we can conjugate that image inside of GLM to go to so that it lands inside of UM. And we can conjugate the image of psi so that it lands inside of UN minus M. And then, yeah, so then we take X to be this block diagonal matrix with X1 and X2, and then you can check. So I didn't spell out the whole, the rest of the argument here, but you can check that it lands, that if we conjugate G by this element X, that we land inside of this subgroup of matrices. And that proves the result because that's just UN. Okay, so yeah, hopefully that's clear. Yeah, we kind of just break it up into the action of G on W and G on V mod W. And that's all we need since we only care about the diagonal elements. Okay, so that's the first case. The second case is where G acts irreducibly on V. And okay, so now we want to embed G inside of, so G already embeds inside of GOV. We want to extend this to an embedding inside the endomorphism algebra of V. So GOV sits inside of NV as invertible endomorphisms. And this endomorphism algebra as an algebraic variety, it's just a vector space k to the n squared. And G embeds inside of there. And now I want to recall a result known as Burnside's theorem. And it says that if we have this sort of situation where V is an irreducible representation of G, then if we take the span of all these elements in the image of this map rho bar, and we take the K span, then we get all of end V. So G itself is not a linear object. G is a group. It's not a vector space, I mean. But then if we look at all look at all the images of all the elements in G, and we make that into a linear object by taking the span of all those elements, then we get all of NV. So that's a result that we'll need. I won't prove it, but this uses the fact that V is irreducible. Okay, so now what do we do? So if we take little g and g, then we know by hypothesis that the G is a unipotent matrix. So then its trace has to be n, because the trace is always the sum of the eigenvalues. So and it's an n by n matrix, so the trace has to be n. Okay, great. So what that means is that, so as a consequence, if we take G, its trace is n. If we take little g, its trace is n. If we take G times H for some other element in the group, then that's still a unipotent matrix, so its trace is still equal to n. So we have that the trace of GH is equal to the trace of G, but that means that we can take the trace of G minus 1 times H, and that'll be equal to 0. So we use the linearity of trace, the compatibility of trace with sums to get this result. Okay, and now we have the following claim that, in fact, if we think of G minus 1 times phi, so before we thought about G minus 1 times H, and we argued that the trace of that is 0, but now we can replace phi by any we can replace H by any endomorphism phi, any endomorphism of V, and that the trace of that product will be equal to 0. And why is that true? Well, that's because of Burnside's theorem. So we can write phi as a linear combination of elements of the form rho G, and then use the additivity of the trace. So okay, so notation wise, I maybe it would have been slightly more precise to write rho bar of G and rho bar of H and so forth, but I think it's still clear. Okay, so
sorry, could I ask something? I just missed one point. Why is the
Sure.
trace of GH is the same as the trace of G?
because they're both equal to n.
Ah, right. They're both
Yeah.
the
Yeah.
product is unipotent as well. Thank you.
Yeah.
Okay.
Yeah. Yeah. So capital G is a subgroup of unipotent matrices. So any product is still in there. Okay. So now we have some operator G minus 1, and if we multiply by any endomorphism, the trace of that product is 0. But in fact, this implies that operator is 0 itself. So, and this is just a little lemma. So if we have any endomorphism and we apply trace of this product. So there's this trace. It's if any of you are familiar with the killing form, this is just the killing form. So if we take any endomorphism and we know that its trace when we take the product with any other endomorphism is 0, then it must be 0. So yeah, and if you don't know this, it's easy to show. So you just pick a basis of V, and then we have a basis for the endomorphism algebra in terms of elementary matrices. So matrices with a single one entry equal to 1 and all the other entries equal to 0. And then if you just write it out, then you get you can convince yourself of this lemma. And yeah, so then how do we use the lemma? Well, we have that G minus 1 times phi, the trace of that is equal to 0. So that means that G minus 1 must be equal to 0. So G is equal to 1. G equals to 1 for all elements in G. And in that case, G is just the trivial group. And it's easy to show that and the trivial group embeds inside of UN. So that's the result. So let me, before asking for questions, let me state the following result. Well, actually, yeah. Any questions about this theorem? I know I'm not going to say anything about the proof of Burnside's theorem, but up to that, I hope the argument is clear.
How do you get this G? Because it said that this is conjugated to UN, but how did you get it?
How did I get which V or?
They say, how do you get the G, the big G?
So big G is by hypothesis a subgroup of unipotent matrices.
Yes, how do you get this? How do you get the G from this? I missed this part.
Yeah, I'm not sure. So, okay, let me scroll back to this is what we're trying to show. So if we have a subgroup of unipotent matrices, then we can conjugate it so that it lands inside of U sub n.
But you didn't conjugate it.
No, so in case 1 where the action is not irreducible, I conjugated it. So, and in the second case where it does act irreducibly, then we show that it's a trivial group. Yeah, but I agree that something feels a bit off with this theorem because If it's a trivial group, then it does not act irreducibly on V. So maybe actually the argument should be that, yeah, maybe there's something fishy about this argument. Let me double check it. But did I address your question?
Yes, that's all. I thought that I
Okay.
missed it. Okay.
Yeah, let me take another look at this theorem. Maybe I'll have something more to say about it next time. But let's move on for now. So one geometric consequence of this theorem is that if we have a unipotent linear algebraic group acting on an affine G space, then all the orbits have to be closed. So so I won't give the proof of this, but it's in Springer. So you can take a look, especially if you think you'll continue and study group actions in algebraic geometry. This is probably a result that you'll come across. The proof is not too hard, but I decided to leave it out. And there's this nice exercise that I will assign. So if you have a subgroup of GLN and it acts irreducibly on k to the n, so the usual action of GLN on k to the n, then its only normal unipotent subgroup is the trivial one. Yeah. Okay, so yeah, I think that's all for the Jordan decomposition for now. One more thing is so the next thing to do is I'll talk about the semi-simple and unipotent parts of in the case of SL2. So I'll give the SL2 example. But any questions about this stuff before I switch to the next PDF?
I have a quick one.
Sure.
Did your answer solve the exercise? This exercise?
Did what?
The answer you told me before about we get a trivial group. Yes, this is the same as this exercise. Okay.
I'm not sure which exercise you have in mind.
This is exercise we are looking at now.
Yeah.
It's related to my question before that we get if it acts irreducibly, if it's irreducible, if it does not have invariant subspaces, then it's the trivial group.
Yeah.
What
Yeah,
we
it's related. Yeah.
the same? Okay.
Yeah. Yeah, but I'm not going to say too much more since I want to give people a chance to think about it. Okay, so
I was wondering if we could have done the same proof, or if we could have done a different proof that's similar to the classification of nilpotent matrices in the typical matrix linear algebra form of Jordan decomposition, where you look at generalized eigenspaces and you subtract one, and then you look at the generalized eigenspace of 0 or of 1, I mean, and then you look at the ones that take exactly n to go to 0 and exactly n minus 1 to go to 0, and you do it that way explicitly.
I think that should work. The problem is that like you can have that may work. The only problem is it's hard to simultaneously put if the elements don't commute. If it's not a commutative group, then you can't put them simultaneously in Jordan form. So as long as you can do it somehow simultaneously, then something like that should work. Or you apply induction. Yeah. Does that make sense?
Yeah, I suppose.
Okay.
I guess you can look at you can just look at all the unipotent matrices at once, subtract one from all of them, and then look at which elements are eliminated or killed by all the nth powers and all the n minus first powers.
Yeah.
N minus seconds and so on.
Yeah, by the different.
But maybe it is possible to prove that there exists an one eigenvector for the entire group, and then there is
Exactly.
an action on the quotient. So
Exactly, yeah. So that's another proof that I kind of had in mind, but then I went with the Springer proof. So yeah, maybe I'll say something about that later. Yeah.
Okay, I was just wondering if there was like any problems with it.
The only thing is, yeah, maybe, yeah, I don't have the full argument. I think, as far as I can tell, it would probably work. Yeah, at least, yeah, I think it's probably fine. Yeah. Okay, so let's talk about SL2. All right, so, oh no, I didn't share it. Oh, wait a minute. There we go. All right, so let's look at the semisimple locus and the unipotent locus for SL2. So, so there's various ways of understanding these parts, and I'll give you one way to do it. There's other ways as well. Okay, so SL2, as we all know, 2 by 2 matrices, determinant is equal to 1. So I'll use this notation. So curly C sub G will be the conjugacy class of an element G in I'll use it generally, but for here it's in SL2. And a note that like we can conjugate by elements in SO2 or in GO2, and we get the same conjugacy class. Okay, so how do we describe the semisimple parts? Or I'll call these the loci. So semisimple locus and unipotent locus. So the first tool we can use is the Jordan decomposition. So if we have a matrix, we can always put it in Jordan canonical form, Jordan normal form. So, and this tells us pretty quickly that the unipotent matrices are the identity and anything that's conjugate to this matrix. So ones along the diagonal, and so this is a single Jordan block of size 2 with eigenvalue 1. So anything conjugate to this will be unipotent, and the conjugacy class of the identity matrix is itself, since it's in the center, commutes with everything. And yeah, so that's the reason. So it's Jordan normal form is either the identity or this. And now, so that tells us already quite a bit about the unipotent locus. What about the semisimple locus? Well, if we have an element, any element in G, it's semisimple if its Jordan normal form is diagonal. And so we have two eigenvalues, their product is 1. So G is conjugate to this diagonal matrix lambda inverse. If it's not semisimple, then there's a single Jordan block with one eigenvalue lambda squared is equal to 1. So it's either in the conjugacy class of this matrix that we saw before, or in a matrix that looks the same except for negative ones along the diagonal. Again, a single Jordan block, because 1 and -1 are the only solutions of this equation, lambda squared is equal to 1. Okay, so now let's think about this case a bit more. There's kind of two subcases. What happens if lambda is equal to lambda inverse, and what happens if they're distinct? So note that lambda is equal to lambda inverse if and only if lambda is plus or minus 1. And in that case, it's in this matrix is in the center. It's a diagonal. It's a diagonal matrix with the same values along the diagonal. And I'm going to assume that the characteristic is not equal to 2, so that 1 and -1 are distinct elements, and so that we can divide by 2 later on. Okay, and so this means that we can, oh, I forgot a close bracket here, but anyway. So this means we can decompose the semisimple locus as so first of all, we have the cases where this matrix is, the Jordan normal form is diagonal with the same entry on the diagonal. So these are central, so their conjugacy classes are just themselves. So we have these two points. And then everything else is conjugate to a matrix, a diagonal matrix with distinct eigenvalues, lambda and lambda inverse. And so these conjugacy classes, they're not just one point. They have more things in them. And we'll set this part to be the regular semisimple locus. So an element is, as we said before, an element is semisimple if it's diagonalizable, and it's regular semisimple if it's diagonalizable with distinct eigenvalues. So yeah, this is a notion that'll come up later. So I'll remind you of this definition later on. But this is we're separating out G sub S into this part where the eigenvalues are distinct and into this part where the eigenvalues are the same. And I'm also going to set negative G sub U to be the negative identity matrix together with the conjugacy class of this matrix, this Jordan block of size 2. And yeah, so this is, yeah, if we take any, I call it G sub U, negative G sub U, because if we take anything in G sub U and multiply it by -1, we get something in minus G sub U. So now we have this decomposition of SL2 into this regular semisimple locus, this unipotent locus, and this negative unipotent locus. And it's disjoint decomposition. And that's because we saw that the whole semisimple locus is the regular one together with these two elements. So these two elements are just the center of SL2 and scalar matrices. So the only two scalar matrices are these two in SL2. And this one belongs to GU, the unipotent locus. This belongs to the negative. Okay. So yeah, so we'll see that this regular semisimple locus is open and the other two are closed. Okay, does that make some sense? All right, so, okay, so that's one tool. The other tool we're going to use is the trace map. So the trace is just the sum of the diagonal entries. I don't know why I wrote X, Y, Z, and W here. I could have just written A, B, C, and D, but we take the sum of the diagonal matrices. So this seems a bit arbitrary maybe, but the reason why it's a good idea is because it's invariant, it's conjugation invariant. So if we conjugate a matrix, so trace has this cyclicity property. So trace of A times B is the same as trace of B times A. So because of that, we have the trace is conjugation invariant. And so it's constant on conjugacy classes. And yeah, and some other observations that follow pretty easily is that the trace is the sum of the eigenvalues of a matrix. And that, so the characteristic polynomial of G is given in terms of, yeah, in this case, it's just, so polynomial of degree 2, t squared minus the trace of G, that's the coefficient on T. And then the constant term is 1 because that's a determinant. So we see that, so right away we see that, so this is a quadratic polynomial. We can figure out using the quadratic formula that it has multiple roots if and only if this discriminant is 0 and the discriminant is 0. So this is a discriminant, trace squared minus 4. So that's equal to 0 if and only if the trace is plus or minus 2. Right, that's what we have here. So that's the trace map. So now I claim the following things. So the regular semisimple locus is the preimage under the trace map of all the points except for plus and minus 2. G sub u is the preimage, is the fiber of the trace map over 2, and minus G sub u is the fiber of the trace map over minus 2. So the decomposition that I said before is can be understood using the trace map. So basically, all the things that we single out 2 and minus 2, we take those fibers, those are G sub u and minus G sub u, we throw them out. What we have left over is the inverse image of the preimage of the trace map of the preimage under the trace map of k minus plus or minus 2, and that's the regular semisimple locus. And that follows pretty easily from what I've said so far. And in particular, this shows that because the trace map is a continuous map, this shows that, and because these points are closed, so this complement of these points is open, this shows that the regular semisimple locus is open, unipotent locus is closed, minus G sub u is also closed. Okay, I think, okay, maybe this is a good time to stop for a break. So I'll pick it up from here in 5 minutes. Okay. Everybody good so far with the assertions I've made about semisimple and unipotent elements in the trace map so far? All right. So, okay, so we saw the regular semisimple elements, unipotent elements, and the negative of the unipotent elements appearing in terms of the trace map. So now let's think about what these fibers actually are. So how do we describe these fibers as algebraic varieties? Okay, so this is the claim. So if we have T and K in the ground field, algebraically closed field, then and characteristic not equal to 2, then the fiber of the trace map over T is the following vanishing locus. So this will be a vanishing locus of a ideal in the polynomial algebra in 4 variables. So this will live in 3 variables. So this will live in K3. So with variables x, y, and z. So it's x squared plus y squared minus z squared minus some constant. So this constant is t minus 2 times t plus 2. So if t is plus or minus 2, then this is 0. But otherwise, this is some constant. In fact, it doesn't matter which constant it is, as long as it's non-zero, we get the same algebraic variety. Okay, so why is this true? Well, let's just compute it. So first of all, the inverse image on the trace map is all the A, B, C, and D in K4 such that the determinant is equal to 1. So this is the condition that it's in SL2. And the trace is equal to T. So A plus D is equal to T. Okay.
Can I ask a question?
Sure, yeah.
Maybe it's simple, but this vanishing set, it has 3 coordinates. I just don't understand because the trace is a map from SL2. Okay, it's 3-dimensional SL2. Okay. Yeah, sure.
Yeah.
Sorry.
So this as an algebraic variety, this will have dimension 2.
Yeah, but I mean, this is the fiber is a subset of SL2, right?
Exactly. Yeah.
But so what are X, Y, and Z in SL2?
Yeah, we'll see. You'll see in just a second.
Okay. Thank you.
Yeah. Yeah, that's a good question. I didn't really say, yeah, but this is just as algebraic varieties, and now we'll see in a second what x, y, and z are in terms of the a, b, c, and d. Okay, so far we have that we have these two equations, but we can make them into one equation by eliminating d. So d is just t minus a, so we put that in here. And now to answer Benjamin's question, we use a change of variables. So we set x equal to 2a minus t. So this change of variables depends on t. We set y to be equal to b plus c and z to be equal to b minus c. And yeah, so this change of variables, it gives us an isomorphic algebraic variety. So it'll be the set of all points x, y, and z in K3, such that this equation holds. So we just do the appropriate replacements, and this is the equation we get. And now we can, yeah, the characteristic is not equal to 2, so we can put all these 2's to the other side. They become a 4 because they all appear twice in each denominator. And we expand out the parentheses, and this is the equation that we get. And yeah, we rewrite it so that the power of x and y is, the coefficient of x and y is +1. And yeah, this is what we get. So the only maybe slightly tricky thing is picking the right change of variables. But once you have that, you get this. And yeah, we can factor this last bit. And so now what does, okay, so now we know we see this isomorphism of algebraic varieties, but what does this look like? Well, let's first consider the cases where we have t is equal to plus or minus 2. So in that case, we have this vanishing of this equation, x squared plus y squared minus z squared. And this, at least over R, is this cone. So we can see that there's a cone point. So the identity matrix will be this cone point, and everything, and there's an action of the multiplicative group that scales everything down to this cone point, and that's in fact the singularity. So we'll talk a bit more about singularities later on, but this variety is non-singular at that point. And similarly, so this is if t is equal to 2. If t is equal to minus 2, the picture is the same, except this point now will be identified with minus the identity matrix. Yeah, so I mean, to understand this picture over R, so I guess x and, yeah, z is going up, and x and y are kind of level, or the horizontal plane. And so then you can see how if z is non-zero number, then we get a circle. That's the slice. Otherwise, if we set x or y to be some number, then we get some non-zero number. Then we get hyperbola when we slice. Okay, so those are the cases where t is equal to plus or minus 2. What about when t is generic? So in this case, t generic will mean not equal to 2 or minus 2. So in that case, we can rescale. We can do another change of variables, if you will, to make this coefficient, this constant term, equal to 1. And then the picture that we get is a hyperboloid. We don't have any more singularities, and we have these 2 points. These 2 points here, which are the 2 diagonal matrices, lambda inverse and lambda inverse lambda. Yeah, so that's the picture over R. So let's put all this together. So if we put this all together, then here's the trace map, SL2 to K. And so K I depict as just a line. So at 2, as we said, we have this the unipotent locus. It's a cone, and it has this cone point, which is the identity matrix. At -2, we have the negative of the unipotent locus. It's also a cone. The cone point is -1. And for generic t, so not equal to plus or minus 2, then we have this hyperboloid, which is just the conjugacy class of lambda inverse. And it contains two diagonal matrices, which are just with the order is reversed. And so we can kind of see how these hyperboloids, when lambda and lambda inverse get close, those 2 points get close together, and when lambda and lambda inverse are the same, then they collide and it becomes just 1 point, which is this cone point here or here. And in terms of the whole semisimple locus is the regular semisimple locus. So all these generic fibers together with these points 1 and -1, the identity and negative identity. And so if you want to think about this some more, you can think about what happens for PSO2 and for GO2. How does this picture look like, or what modifications need to be made for these two groups? Okay, so I hope that was helpful. So yeah, go ahead.
I have a question about the picture. Can you see in the picture the conjugacy class, the conjugacy classes?
The conjugacy classes?
Yes. Can you see this in the picture? Is it the same height? What does it mean?
Yeah, so each one of these generic fibers is a conjugacy class. And
with respect to the height, right?
It's with respect to what?
With the height, to the distance from the floor.
The height?
Yes.
I'm not sure what you mean.
Which fibers do you mean?
So every generic fiber is a distinct conjugacy class. And then
okay. Oh, thank you. No.
And then at 2 and -2, we actually have two conjugacy classes. One is the conjugacy class of just the identity matrix, which is just 1 point since it's central. And the rest of it is the conjugacy class of this upper triangle 1, 1, 0, 1 matrix. And for here, it's the same thing, but -1, 1, 0, -1, which is actually the same as the conjugacy class of the matrix -1, -1, 0, -1. Yeah. Does that answer your question, Tal?
Yes. Thank you.
Okay, great. All right. So yeah, that's kind of nice. Any other questions? Okay. All right. So I think let's move on to the next PDF then. We're making good progress today. Hopefully it's not too fast. If it is, just slow me down.
Maybe you can say something about what this picture, I mean, does it teach us something, or it's nice to know how these things work?
Does it what? Does it?
Just knowing, looking at this, I mean, on this drawing of the fibers, what can we learn about, I don't know, about the group or about anything?
Yeah, we can learn a lot of things, but maybe, so it'll be more instructive later on in the course. Maybe right now it doesn't seem super enlightening, but later on this sort of construction will be quite useful. Let me just say one thing for now. So there was this cone point, this unipotent cone with a cone point. So there's ways to resolve this cone point. So there's this thing known as the Grothendieck-Springer simultaneous resolution, which resolves these cone points, and you get a family where all the things are smooth, and that has applications to representation theory. That eventually gives you a way to kind of understand the representations. But I don't know if we'll actually get to that in this class. Yeah, so that's one answer, and I think later on we'll see other answers. Yeah.
Do you also have a question about those two fibers, -2 and 2? You said that they are closed points. So if I want to imagine the group as a manifold, so they correspond to boundaries or something. You in the right one, this is the open part, but those are
I don't think so. Like, you can think of them as boundaries of maybe of the semi-simple locus, regular semi-simple locus, but it's not really. I wouldn't say it's the boundary of the group. No, I wouldn't say the group has any boundary.
we cannot identify this group as you cannot draw the picture without dividing by traces. You cannot picture SL2 without dividing to 3 sets.
Oh, you mean what happens if the characteristic is equal to 2? Is that the question?
No, I mean you splitted the variety. It's very splitted the algebraic group 3 parts, and you say each one has its own variety. But can't you see this as sub-variety of the general one?
For a general linear algebraic group, you mean?
No, for SL2 as a one variety. How does the picture, is it related to the picture of SL2 as a one-piece variety, not 3 varieties?
Well, it is one piece. I mean, these are all glued together.
Yes, how? This is my question. How? This is...
Well, I think the picture kind of tells you how. Like, you have this map on SL2, and anytime you have any map, the original thing is glued from the fibers. And this is a particularly nice map because the generic fibers all look the same. And there's some special fibers that have singularities, but they're the same dimension. And you just kind of smash 2 points. You identify 2 points. You smash that circle in the middle for the generic fiber to get the singular fibers. And yeah, I mean, I think, yeah, the picture itself kind of tells you how things are glued together. Yeah, I don't know if that's helpful, but that's kind of what's happening.
You can see just a stratification of the group from this picture. So maybe Tal, if you're interested in what this is called.
Yes, there is another dimension. Okay, this is the dimension of the trace is another dimension. Okay. You take the fiber.
Yeah, and yeah, it is a stratification in terms of the fibers. You can also think of it as a stratification of the regular semi-simple part, which is an open subset, and then you have some extra closed stuff. That's the unipotent part and the negative of the unipotent part. Yeah. Okay, so yeah, any more questions? I'm glad you guys are interested in this picture. Okay, so then let's move to the next chapter, I guess, which is about commutative algebraic groups. So we'll still need some, we'll still be using a lot of the Jordan decomposition stuff, but this will be a little bit in a different flavor. So commutative algebraic groups, so algebraic groups where all the elements commute. So before jumping in, let's state this lemma that we'll need. So if we have a subset of pairwise commuting matrices, then, so it doesn't need to be a subgroup, just some subset of matrices that commute. then we can always put them in upper triangular form. We can always conjugate all the matrices by the same element such that they all become upper triangular. So yeah, so that's one thing. And then if they all happen to be semi-simple, aka diagonalizable, then we can find an element so that when we conjugate each of them, they become diagonal. So it's very important that they commute. So I think I asked you guys to maybe think about this lemma a little bit as an optional exercise. So let me just give a sketch of what's going on. So again, it's induction. It'll be similar to that proof about unipotent matrices that I stated earlier. So it comes down to two cases. So first of all, if S is just scalar matrices, scalar multiples of the identity matrix, then there's nothing to show since they're already diagonal, in particular upper triangular. If they're not, then there is a matrix and an eigenvalue for that matrix, so that the eigenspace is some proper non-trivial subspace of k to the n. So the dimension of this eigenspace is somewhere between 0 and n, not inclusive. Okay, so let's say W is this eigenspace. So the eigenspace is for all the lambdath eigenspace of this element S in little s and big S. One thing to note is that this eigenspace, because S commutes with everything else, little s commutes with everything else in big S, this W will be stable under all the elements in big S. Okay, so what do we do now? We take this W, we pick a basis for it and extend it to V. Then S is, so this is similar to before, S is contained in these block upper triangular matrices. As I pointed out before, if we have any other little t and S, then you can just write it out and see that W, this eigenspace, is stable for any t. And so now we can apply induction, so it's similar to what we saw before, and we can put this part in upper triangular form, so we put it here, and we put this lower part in upper triangular form, so it's like this, and so then the whole thing is in upper triangular form. Hopefully this is clear. If not, then you can work out the details. It's not anything super deep, it's just linear algebra. Okay, so we have that. So now I want to state one more result. So first of all, we need the commutator subgroup. So this is the subgroup generated by all the commutators. So the commutator of two elements x and y is this product xy, x inverse, y inverse. So it's a normal subgroup and the quotient is commutative. Since this commutator measures the obstruction to two elements commuting, and it's equal to the identity if and only if they commute. So if we mod out by all the obstructions for commutativity, then we get something commutative. And G itself is commutative if and only if this commutator is just identity. Okay, so probably you've seen this before. Okay, so what do we need to know about commutators? Well, so this is the lemma. So if we have UN, the subgroup of upper triangular matrices with ones along the diagonal, then I'm going to set. This is just notation. So U square bracket 0 is just U itself. And then UN square brackets K is the commutator of UK minus 1 and UK minus 1. So U square brackets 1 is just the commutator of U. Okay, and then the claim is that if we do this process n times, if we take successive commutators n times, then we just get the identity, the trivial group. So why is that? Well, it's pretty easy to show. So let me just tell you what the kind of the trick is, and then you can fill out the details. So
Wouldn't it suffice wouldn't it suffice to take UN without power in one of them?
I think, yeah, so I think that's, yeah, so this is like the lower central series, and then you have the upper central series. So if you don't take powers, then yeah, I think it's true. So I always get confused about this. So for one of them, it's the Borel that you need to take that you need to take one of them without. So there's the idea of an abstract group being nilpotent and an abstract group being solvable. This shows that it's nilpotent, but yeah, if it's nilpotent, that it's solvable. Yeah, so then you can indeed take just the commutator in one component. And the Borel subgroup will be solvable, but not nilpotent as an abstract group. Yeah, but it's easier to see it from this perspective. Does that answer the question?
I think so. Yeah, thanks.
Okay. But even in that case, maybe this sort of argument still works. So anyway, the argument is the following. So if we take the commutator once, then we'll still have ones along the diagonal, but zeros along the super diagonal. And if we take a k times, then we have these k diagonals all being zero, and we still have some stuff here. And so so you basically, I guess, by induction show that this is true. And then so if we take n steps, then we fill out all this with zeros, and we just have the identity matrix. All right. Okay, so yeah, so now here's the actual result we wanna show. So we'll use these two facts in a bit. So okay, so if we have a commutative linear algebraic group, then as in any algebraic group, linear algebraic group, we have the semisimple locus and the unipotent locus. But if it's commutative, then the claim is that these are closed subgroups of G. So before with SL2, maybe I could have pointed out that these G sub U and G sub S, they're not subgroups. And G sub S, as we saw, was not closed. G sub U was closed. In fact, G sub U is always closed. That's one of the exercises that I'll assign for this week. G sub S is not closed in general, but if the group is commutative, then they're both closed and they're both subgroups. So that's kind of strong. And in fact, G itself is, as a group, is a product of GS and GU. So this multiplication map is an isomorphism of algebraic groups. So yeah, so for commutative algebraic groups, all you need is the Jordan decomposition, and then knowing things about commutative diagonalizable groups and commutative unipotent groups. Okay, so how does this proof go? So yeah, as I said before, G sub U is closed in any linear algebraic group. That's something you guys can show. And we need to show, oops, sorry about this. We need to show that it's a subgroup. So we saw a variant of this argument before. So if we let's take two elements G and H that are unipotent, and we can take an M large enough so that G minus 1 to the M is equal to 0, as is H minus 1 to the M. So this is just a definition of being unipotent. We can, G minus 1 is nilpotent, so we can have this. And then we use binomial expansion to show that G times H minus 1 to the 2M is equal to 0. And we can use the binomial formula because they commute, so everything's fine. Yeah, I won't spell out the argument, but the first step is to write GH minus 1 is G minus 1 times H plus H minus 1, and then this is the thing you apply the binomial expansion too.
What do you mean by GH minus 1? You have only group multiplication.
Yeah.
How do you add how do you add minus 1?
So I guess that's a good point.
Is this a
So
representation?
yeah, I guess you embed it. You have to embed it. Yeah, that's a good point. I think you embed it. Yeah, you pick an embedding of G inside of GLN, and then you do this. Yeah, that's a good point. Thanks. Okay, so that takes care of the unipotent unipotent locus. So yeah, the key it's simple because it's already closed, and then the commutativity tells you that it's a subgroup. You can also, I think, use the lemma from before, but anyway. So so what about the semi-simple locus? So this will be maybe slightly more involved. So let's embed G into GLN, as we can always do. So first of all, the product, so showing that it's a subgroup is easy, because we know that commuting matrices are simultaneously, commuting diagonalizable matrices are simultaneously diagonalizable. So the product is again in GS, so it follows that GS is a subgroup. We just need to show that it's closed. Okay, so how do we do this? So okay, so since all the elements in GS are simultaneously diagonalizable, that's the lemma from the start of the lecture. I only proved one part of the lemma, but the second part is kind of the same argument. And so, okay, so since they're all simultaneously diagonalizable, we can pick a basis for V. So V, I guess, is K to the N here. Yeah, we embed it inside of GLN, and I guess I should have said V is K to the N. We can pick a basis where all these matrices are diagonal. So for every G, there's some scalar that I'm going to call phi sub I of G, such that G acts on VI with this scalar. So we have a map VI, group homomorphism VI from the semi-simple locus to the multiplicative group. Okay, so and now in this basis, so now the claim is that in this basis, the semi-simple locus is just all the matrices, all the elements of G that are diagonal matrices in this embedding. And why is that true? Well, first of all, anything in G sub S will be a diagonal matrix, because by construction we chose these VIs. And on the other hand, if we had something that's in G and a diagonal matrix, then we know that it has to be semi-simple, because we had this result earlier today that says that anytime you embed a group inside GLN, then any semi-simple element gets mapped to a semi-simple element of GLN. In other words, a diagonalizable element. This is actually stronger. It's not only diagonalizable, it's already diagonal. Yeah, so that you think about it, and it becomes clear that these coincide. And so that proves that GS is closed, because it's the intersection of G with a closed subgroup of GLN. And G is, yeah, so that proves that it's closed. Okay, so that's, yeah, I think this theorem is not too deep. It's just some more linear algebra like we've been doing. Okay, and the second part follows because the only thing that's both semi-simple and unipotent is the identity. So that's the only thing that's in the kernel of that map. So the map it's surjective and it's an isomorphism. Okay, any questions about this theorem or its proof? Yeah, it's just linear algebra. Okay, so what do we have here? Okay, so next we want to show the following. Let's see, how am I on time? Okay, so
I have a tiny question.
sure.
For what you showed before.
Mhm.
Why, if you're not talking at the level of algebraic group homomorphisms, but just group homomorphisms, so it seems that you can say, what is wrong with saying that every such linear group is a direct product of the unipotent and the semisimple? What is wrong about this? Because you have a unique representation as a multiplication that is a commute. You can switch the order of the elements. So it is a multiplication.
Well, this says that every semisimple, so that would be true if every semisimple element commuted with every unipotent element.
And it's not for any.
And
Okay,
that's not true in general. No.
Okay, only for specific one. Okay.
Yeah, yeah. So it's quite strong that we have something that's commutative. Okay, so let me state this proposition. Maybe say start the proof, but I think we'll probably stop soon and not finish the whole proof. So, okay, so what does proposition say? Well, let's say we have a connected linear algebraic group and it has dimension 1. Then necessarily the group is commutative. So, so somehow this dimension constraint doesn't let elements commute in a non-trivial way. So they just commute. So that's the first thing. So then either G is equal to its semisimple part or it's equal to its unipotent part. So those will be, by part 1, those will be commutative linear algebraic groups of dimension 1, or yeah, dimension 1. So, okay, so the proof that's given in Springer is a proof by contradiction, but I wanted to point out this statement that I read when I was an undergrad in a real analysis book by Royden. All students are enjoined in the strongest possible terms to issue proofs by contradiction. So this became kind of ingrained in me. So I have this allergy towards proofs by contradiction now. So I'm going to try to rephrase. It's basically the same proof, but I'm rephrasing it so that it shows something positive, not doesn't lead to a contradiction. Okay, so so the way to do it is let's suppose G is not commutative and has dimension less than or equal to 1. Then we show that in fact the dimension of G is equal to 0. And that shows the contrapositive that if the dimension is equal to 1, then it's commutative. Okay, so right. So okay, so since G is not commutative, there's a conjugacy class that's non-trivial, right? So there's some element G and some element H where this conjugating by G doesn't give you, oh, this should be, it's not equal to just G itself. Let me fix that. Yeah, so there's some element in G that takes this little g somewhere else. It doesn't leave it at G. And now since this conjugacy class is closed and irreducible, and since it's it's not equal to just 1 point. So let me paste this. So the dimension considerations and dimension assumptions that it's less than or equal to 1 mean that its closure has to be all of G. And moreover, the complement, so G minus this conjugacy class, is finite. So it's so G itself is this conjugacy class together with some other element G1 through Gm, finitely many. And the next thing to do is to embed G inside of GLN and to look at the characteristic polynomial map. So this is the map that takes Y and G to the determinant of T times the identity n by n matrix minus Y. And so this will be something of degree n. I could have just said, yeah, so if you want to think of this as landing in a vector space, this lands in the vector space of all polynomials of degree less than or equal to n. In fact, we could have said degree equal to n, but it's okay. So yeah, so this is the map that takes Y to its characteristic polynomial. And now the image, so we'll show that the image actually has to be finite. And this comes down to the fact that the characteristic polynomial is constant on conjugacy classes. So the image of the characteristic polynomial map is that of T minus Y for Y and G. So we know that everything in G is either one of these finitely many G sub i's, so there's finitely many things here, or it's in the conjugacy class of this little g that we chose before. But the determinant is a conjugacy class. If we take any conjugate of little g, then it has the same characteristic polynomial. So then the image must be finite. There's the characteristic polynomial of little g, and then these other characteristic polynomials. And since G is connected and this characteristic polynomial map is a map of varieties, we see that the image is finite, so it's disconnected. So we see that the image must be actually well, it's finite, so it has to be connected because G is connected. So in fact, every element in G has the same characteristic polynomial as the identity in G, and the identity has the characteristic polynomial T minus 1 to the n. So remember that we embedded G inside of GLN. So this n could vary depending on our embedding. It's not something that is determined by G. But anyway, we have that the characteristic polynomial of any element in G is T minus 1 to the n. And that means that 1 is the only eigenvalue of any element in G. So G must be unipotent. And we have this result that we can assume that G is, by changing the basis if necessary, that G is in UN, upper triangular matrices with ones along the diagonal. And now we use this result about the derived subgroups, the commutator subgroups. And we know that the successive commutators of these UNs is 0 eventually. So that implies that the same is true for G. But now so it means that when we take the commutator of G, we must get something smaller, since if we take successive commutators, we'll eventually get to the identity, to just the trivial group. So we must get something smaller. But since it's a proper closed subgroup of G, and it's also connected, it must be just the trivial subgroup, since it has to have dimension 0. If G has dimension 1, then it has to have dimension 0. If G has dimension 0, then again, it's dimension 0. So there we go. So the commutator has to be trivial. But if the commutator is trivial, then the group has to be commutative. But you can also, I think we're actually done here, but you can still go through this argument that G is this disjoint union of the conjugacy class together with these finitely many things. And then the conjugacy class you can write as G inverse times the conjugacy class times G. And now G inverse times the conjugacy class is something that lives inside the commutator. And the commutator is just trivial. So it turns out that G is just these finitely many things. But then G has dimension 0. But I think we're actually done here. Once we show that G is trivial, the commutator is trivial. So yeah, I think this is a good stopping point. Maybe I'll say some things about this proof next time because I went through it kind of quickly. All right, any questions? Okay. So yeah, so I'll say a bit about this. I'll go over this proof again a little bit next time, and yeah, then we'll continue, and I'll send an email in the next few hours with the exercises for this week. All right, thanks everybody.
You're done?
Thank
Yeah.
you.
Mm-hmm.
Yeah, I do have actually a question, but kind of about the map trace T and the fibers.
Sure.
Just not about the material though. But
Sure.
I see that it's not Morse, right? Because the singular fibers are like not discrete.
Yeah.
So I have two questions though. So the first is kind of, is there a famous class of functions from the differential